The resolution of a vector is an important process of understanding the effect of a force in a particular direction. Say, for example, I just give a brief thing, I'll elaborate on that. So this is an inclined plane, and here there is a body on that. And there is a force of gravity acting on it, given by the earth. But as you are aware, the block can only come down, slide down along in this direction. So what we need to know is that the effect, or rather the part of the mg that is influencing the motion of this block in this direction, say we want to know how much part of this mg is available here to cause the acceleration of the block down the incline. So what we require here is to break up mg into two components. I just already am using technical terms, so I shall come to that step by step. But you already knew what I want to say. I want to say resolution of a vector is a process that will help us to break a force into two or more components and investigate their roles in particular direction which may be different from their own direction. So first of all, the definition. The resolution of a vector is the process of determining a set of vectors which produce together the same effect as the original vector does alone. Each vector in the set is known as a component vector of the original vector. Although I shall deal with this in much more detail, but to give you a very brief idea with the definition by the side, say for example this is a force and I could break it into two component vectors. So this one, let me call the x component vector, and this is the y component vector. So they together would produce the same effect on any body as f would have done alone. Now we shall learn, if we divide or resolve f into these components x and y, or even more of them, what will be the values of fx and fy in terms of f and all these things. So we shall learn all these things step by step, but first of all we will just know one thing, that resolution is a process that is opposite of vector addition. Now I hope you have learned about vector addition. In any case, I shall quickly recap that before we teach further. When you do vector addition, for example, say, suppose, let me take many different cases. For example, if there are quite a few vectors and I could add them n to n like that. So the vector sum, the addition, the resultant of them would be given by the closing side of this polygon. This is the polygon rule of addition. So see, I am doing it for some purpose here to show the reversal of this. If say f1, f2, f3 and f4, they were added, and then the resultant, that is the summation of them, vector sum, that we might call R. So R would be given by f1 plus f2 plus f3 plus f4. This is vector addition by polygon rule. So once we know this, and I tell you that resolution is opposite of that, so what does it mean? Suppose you have been given one original vector like that, and you need to break it up into component vectors which together would have given the same result or same effect will produce on the body. So if you just reverse the polygon law, what you could have done is this: you have to just construct any possible polygon. I can even add as many as I need. Look here, unlike the first case, R is given to you and you yourself choosing the number of component vectors arbitrarily. So suppose these F1, F2, F3 defined by you because you are aware that the magnitudes of the forces given by the length of these arrows and the directions is given by the arrow cap. So I could say that I have resolved R into 6 components. It is sort of a reversal of Polygon rule, what I have done, but there is nothing wrong about it. Here F1 through F6, these 6 forces in green arrows, would produce the same result or the same effect on a body as R does alone, which follows as a corollary of the Polygon law of vector addition. You might say, why only this? Any other possibility is okay. That's correct. I could even draw a figure like this. It's absolutely fine. Suppose I define a set of 3 forces, F1 dash, F2 dash and F3 dash, so that once again the first one's tail is coinciding with the original vector R's tail, and the third one, F2 dash, is somewhere midway, and F3 dash, the last one's head, coincides with the head of the original vector R. So that way also is a Polygon law. So either I could also write, R could also be written as F1 dash plus F2 dash plus F3 dash, provided you make sure that the component vectors are chosen in such a way the first one's tail coincides with the original's tail and the final one's head coincides with the original's head. In such case, you can take any number of combinations of component vectors which can give you the original vector thanks to the Polygon rule, but applied in a reverse manner. So that is the first example of resolution where I have broken down R into many component vectors by applying Polygon law in reverse. I think a more specific example where we have got a mathematical formula to apply and find the magnitude of the component vectors we shall do next. Suppose there are any 2 arbitrary directions given. Let me use some thinner ink than this. And a vector that is the original one is given as this. This one is my original vector R, and I need to resolve it into 2 components along these white lines. This is O, the origin. One line, let me call that OM, and the other line I call it ON. And this R vector is making an angle of alpha and beta with these 2 lines OM and ON. Now my intention is to break this R, or resolve the R rather, let me use the technical term, resolve R into 2 component vectors, one along OM direction and other along the ON direction, so that those component vectors together will be equal to R, or they will produce the same effect as R does alone. So what we do in this case, we just complete the parallelogram as I'll show you here. From the tip of R, I draw a line parallel to OM which cuts ON at a point, Similarly, from the tip I draw another line parallel to ON, which cuts the line OM at a point. It's important that I should be giving names of them as well. So the original vector R, let me call that OA. A is the tip of it, O was of course the tail, and the foot of the line drawn from A on OM, I am calling it B, and similarly on ON, the foot of the line drawn is called C. So I shall establish with the help of triangle law that you have done in vector addition, that if I could call this OB thing as vector P and OC thing as vector Q, so as I have drawn those lines, I shall prove that if OB was called P vector and OC was called Q vector, I shall prove here that the original vector R resolved into the two parts is given by P plus Q. That is, P, vector P, as you can see, that is same thing as OB vector, is the component vector of R along OM, and Q vector, that is OC vector, is the component vector of R along ON. Proof is not very difficult to see. You are aware of triangle law that I want to mention very briefly here for a quick recollection. The triangle law says that if two vectors are represented by two sides in the same order, so that the head of the first one and the tail of second one is matching, then the closing side of the triangle taken in the reverse order will give the resultant. So let's repeat once again. If P is one vector and Q was another vector and they have been joined end to end, this is important, that P's head coincides with Q's tail. In that case, join the tail of P to the head of Q in the reverse order. This will give you the resultant of P and Q. This is the resultant. Now that is the triangle law of vector addition. And as I have already said, resolution is the process that is opposite of addition. My job is to do the opposite of that. Suppose here R was given, and I wanted to break it up into two component vectors P and Q. So I first notice that. Let's see how we can prove the result with the triangle law very much in mind. We consider the triangle OAB, and in the triangle OAB we can simply see by applying triangle law that OB plus BA must be giving my OA. I have drawn the triangle law only by the side for a quick comparison. That is exactly what I have done on the right side. OB plus BA, this is the, of course, BA vector, that is equal to OA. But this means OB is nothing but P vector, and BA, note here, BA is same thing as OC, because in a parallelogram BA and OC, their opposite sides, they have the same length and they have the parallel direction as well. So if two vectors have got exactly same length, the arrows, and they have the same or parallel line of support and the same sense as in the case of BA and OC, then BA and OC must be equal vectors. So I could replace this BA thing by OC actually, and that is same thing as Q. So I am writing here once again that BA vector the BA vector and OC vector, they are equal vectors since they have the same length and they have the same sense as well, because they are parallel opposite sides of a parallelogram. But OC is Q, so P plus Q is giving me OA, that is nothing but R. So I have been able to prove the result that P plus Q is equal to R, and in reverse way R must be given by P plus Q, that in my figure is OB plus OC. So I have established that OB, once again, OB or P is the component vector of R along OM, an arbitrary direction, and Q vector or OC is the component vector of R along ON, another arbitrary direction, and these two directions are making angles of alpha and beta with R. So once you graphically establish that OB and OC to be these component vectors along OM and ON, my next job is to find out what is the magnitude of P and Q. So we shall now try to find out the magnitude of the P vector. That is same thing as saying P here is OB vector. We could also write, these notations we can also write like that. We can just also write simply P, or you can write OB and so on. But I shall stick to this one first. That will be helpful. We also need to find out what is the magnitude of Q vector, the another component vector, because we have been given the magnitude of R is known and the angle alpha, beta are these things are known. So my job is to find out the values of P and Q, these two component vectors, magnitudes, in terms of the magnitude of original vector R and the angles alpha and beta made by it with OM and ON direction. But for that we require a different, cleaner figure. So we start with more or less the same figure on a fresh page, and you see that, quickly saying what I have said earlier, the original vector was R, represented by OA. OM and ON were the two arbitrary lines. Angles made by them was alpha and beta with R. I resolved R into two components, OB or P and OC or Q, by drawing a parallelogram. And we intend to find out the value or magnitude of P and Q numerically in terms of R, alpha and beta. First of all, let's recollect quickly a simple formula of sine, the law of sine of trigonometry, which I assume you have known, but in any case I shall tell you that. In any triangle ABC, opposite to angle capital A is small a and small b and small c and so on. So it can be shown that A upon sine, this is called law of sines, A by sine A was of course the length BC of the side BC opposite to the angle A. This was angle A, capital letter, and small a for the length of the side opposite to angle capital A. Similarly, B by sine B is equal to C by sine C. This is the law of sines. Law of sines. A familiar formula in trigonometry. Now, looking back at our figure, we can notice that if we could take the triangle OAB, in such case, this angle also happens to be beta. It's an alternate angle because OC and BA, they are parallel and OA cuts them. So now let's take the triangle OAB, and if we apply that law of sines shown on the right side, we could have written down length of any side divided by sine of the opposite angle. You note yourself and confirm what I am writing. Don't see blindly. OB, the length of that side OB. I didn't put an arrow there because arrow means vector. When I write simply OB, it means the length of that arrow OB. That is the magnitude of the P vector. So OB by sine beta, then BA by sine alpha. The same logic here, any side length divided by sine of the angle opposite to that. And the third side left is of course OA divided by, we are looking for here this angle. This angle obviously is 180 degree minus alpha minus beta. Is not it? In a triangle, three sides, three angles together is 180 degree. So it's 180 minus alpha minus beta. This angle. So I write here sine of 180 degree minus alpha plus beta, like this. Now since I already know that the length OB is nothing but the length of the arrow representing P vector, OB is the magnitude of P vector, that is just P. I told you earlier in the previous page, if P is a vector, its magnitude can be expressed by either this symbol, modulus symbol, or just simply by P. Similarly, the vector Q, I can express that either modulus symbol or just simply by Q, and similarly for R as well. So we are getting P divided by sine beta is equal to, once again, BA. BA is same as OC, and the length of OC is nothing but the magnitude of the Q vector divided by sine alpha is equal to OA, that is the length of R vector, so the magnitude is R, and this is sine 180 minus theta is sine theta. We know it, sine 180 minus theta is sine theta, so we simply write sine alpha plus beta using the formula of trigonometry. From here we are getting the result that we want to show here in this page only. So let me highlight that somewhere above, and we are getting the value of P is coming out to be R, magnitude of original vector R, into sine of the angle beta, that is the angle between R and the other side, that is Q, OC, divided by sine alpha plus beta. Similarly, Q is coming out to be magnitude of R into sine alpha divided by sine alpha plus beta. So looking back here, I have written down P and Q inside a box because as I didn't have much space here in this page, I had to show it in a highlighted way because this is the result I'm looking for. Let's look at these formulas I have got just now. Our job was, let me sum up what we have done. R was the original vector. Two directions were given, OM and ON, at an angle alpha and beta respectively with R. We wish to find out component vectors of R along OM and ON so that those component vectors P and Q would produce the same effect on any body as original vector R does alone, because that is called resolution of R into two vectors P and Q in two arbitrary directions OM and ON. We first showed R is same as OB plus BA by triangle law, and then using BA as same as OC, we argued that R must be equal to OB and OC. But then OB is named P and OC is named Q, and by using the law of sines, we have established that the magnitude of P which makes an angle of alpha with r, is given by r, that is magnitude of the original vector, multiplied by sine of the angle beta, that is the angle between r and the other component vector, not the p1. Here alpha was the angle, note carefully, here alpha was the angle between r and p, and beta was the angle between r and q. So when we write p, I use beta, sine beta, beta being the angle between r and the other vector, that is q, by sine alpha plus beta. And similarly, q is coming out to be r, that is magnitude, into sine alpha, that is the angle between r and p, by sine alpha plus beta. So this is the result we have got for the magnitudes of b and q, which are component vectors of r in two arbitrary directions. I shall give here a quick problem for you that you should solve in yourself. Let me give a problem for you here. Suppose it is given that r is equal to 10 Newton and alpha is equal to 45 degree and beta is equal to 60 degree. You will find out the value of p and q. That is your job. So I shall give you the answer of this question sometime later, but first of all let me give you the problem. Once again, r was given as 10 Newton, alpha was 45 degree, beta 60 degree. Find the value of p and q. This ready-made formula is there for you in the red box. Apply that and confirm the results given in due course. Okay. My next job will be to resolve r into two component vectors along two mutually perpendicular directions, say x and y axis. That is the most familiar case, and we shall go there very shortly now. Let us draw a coordinate system where the two axes are mutually perpendicular. This of course reminds you of the OXY coordinate system. This is the origin where the two axes meet. This is my x-axis and this is my y-axis. And suppose the original vector r, that was given like this. This was my r vector. The vector r is subtending an angle theta with the x-axis. So obviously, since we have said x and y are mutually perpendicular, you can easily conclude that the other angle must be 90 degree minus theta. And here again my job is to resolve r into two component vectors along x and y directions. So quickly remembering what we have done a short time back, that was actually a more general case. You remember very well that there were two arbitrary directions OM and ON, and the vector r was something like this, and you resolved it by drawing, yes, by lines parallel to the two axes. This is what we had done. I'm just drawing freehand to just remind you what we have done, and we found this one and this one became the component vectors. So here you do the same thing, but the figure looks more elegant obviously for very obvious reasons. So what you do is that you drop a perpendicular from the tip of r onto the x-axis, that is parallel to the y-axis, and again you drop a perpendicular from the tip of r onto y-axis, that's parallel to the x-axis, and also give the proper letterings here also. This is A, I call it. OA is the r vector. perpendicular drop is called AB on x-axis, and on the y-axis we call it AC. So here again I can see here there are two component vectors coming here. This one I will be calling x component, or Rx, let me call that, is the x component vector of R, and along the y-axis I have Ry, y component vector of R. So it's like this. So we are not calling it P and Q intentionally, we are calling it Rx and Ry. So obviously we can write in the same way that since we resolved R into these two components, you can establish easily by triangle rule that was done by me shortly back. R is given as Rx component vector and Ry component vector. Actually you can write this as Rx component, that is a scalar quantity, into I cap being the unit vector along plus x axis. Similarly, Ry vector has a magnitude of Ry into j cap, this j cap being the unit vector in the plus y direction. Of course, Rx and Ry, they are called components. Look at this difference of terms. Rx is component vector here with the arrow on top, and the magnitude of that is just x component. Ry with an arrow is the y component vector, but its magnitude is just y component, Ry without the arrow. But I must have used I and j, these two unit vectors, to retain the vector characteristics of these two component vectors. So once we have got R is equal to Rx plus Ry, obviously we should find out what Rx is, but that is a very easy job, because you can simply apply in the triangle OAB, which is a right angle triangle now, unlike the previous case. OAB is a right angle triangle. Here I can write cos theta, you know, is base by hypotenuse, so that is coming out to be the length OB, that is base, by hypotenuse, that is OA, and that is giving me OB, which incidentally is nothing but the magnitude of Rx vector, that is coming out to be OA cos theta, OA cos theta, but OA once again is the length of R vector, which means it is magnitude of R. So Rx is R cos theta, that is my first result. And if I apply the case of sine theta in the same triangle, that is perpendicular AB, that is opposite, by hypotenuse OA, which gives me AB. The length AB, once again you can easily see that is same length as OC, because AB and OC, they are parallel and they have the same length because they are opposite sides of an rectangle. So AB thing is coming out to be same as OC, but then OC thing is same as Ry, and this is equal to OA sine theta, that is R sine theta. I shall write the result cleanly, but just have a look and don't lose concentration here. I have established by simple trigonometry without much ado. I didn't require the law of sines, unlike the previous case. I got the length OB that represents the magnitude of x component, that is Rx vector, as R cos theta, and the y component Ry magnitude was found to be R sine theta, while the angle theta was defined in my figure. Once again, let me write these results quite prominently on the top. We have got shortage of space here, but I shall write it. We have got Rx, the x component of the vector r after resolution is given by magnitude of r into cos of the angle made between the x-axis and the r vector, and similarly ry was found to be magnitude of r into sine theta. Remember, theta is always the angle with the x-axis of r, not with the y-axis. It comes automatically by simple trigonometry. We shall highlight this box to make it very prominent because this is the result we are looking for. So that's the result we have just now got, and we can just proceed from here and write a few more things which I shall show. Rather, I can just take off a small portion of my writing and write there for our benefit. We could write that the vector r as you can see, the vector r can be written as rx I cap plus ry j cap, which I wrote earlier even. Same thing I am writing. Now that is same thing as writing r cos theta, that is our newfound result, I cap plus r sin theta j cap. This is the way you could express with the help of unit vectors I and j. So that is one way of writing. You can also see by reverse process, incidentally, that I leave for you as an exercise. If rx and ry were known, you can go by the reverse way and could show that r is given by we can add some more results here, and I could write down that if rx and ry were known, you should be able to show that r is equal to square root of rx square plus ry square. That you must be showing. And similarly, if r makes an angle of theta with the x-axis, you should show tan theta is equal to ry by rx. This last two results is if you already know ry and rx and you need to find out r and the theta. So all these results you can get yourself. We have done up to this, and the last two results I have told you to prove, because these show that if the component vectors are known, you can, in the reverse way, conversely you can find out the original vector as well as the angle it makes with the x-axis. So this is your job. Incidentally, going back to the previous question, I just want to tell you the answers of the questions, the one I gave earlier. So the question that I gave earlier, problem number 1, is back here. I said the answer of the questions. The answer is P is 8.97 Newton and the value of Q is 7.32 Newton. I'm sure you have got the results. Let us take one problem to understand this, what we have learned just now about vector resolution, right? So suppose in a problem it's given that, so the problem given, the x and y components of a vector P, the vector was named P, and its components, that is x component, is given as 4 root 3 meter. So obviously P is a displacement vector, and y component of P is minus 4 meter. Look at this minus sign, that will be significant for us. The question is, what is the magnitude of this P vector, that is of course just P writing, and what is the angle made by P with the positive x-axis? With the positive x-axis. So let's do this problem. First of all, since I gave you as an exercise a little earlier, so you know that P is given by simply square root of px square plus py square. This is the magnitude of P. So just put the values. It's 4 root 3, the first one, px square plus minus 4, we keep it as it is, but squaring the whole quantity becomes now positive. Square rooting this quantity, this is coming out to be how much? Tell me. You can check it. This is coming out to be 8 meter. And to find out the angle which this P vector is making with the plus x-axis, let us draw a coordinate system. So this is my coordinate system, as you can see, and this is my plus x direction, this is minus x, this is plus y, and this is minus y. Here it's important to know about plus and minus signs, because you have noted that we have px as positive and py as negative. Now what does it mean? This, of course, as you can see on the screen here, well, this must be my px. This is the x component of the vector p, and I must point in the plus x direction because its magnitude is 4 root 3 meter, a positive value. So let us write, this is my px. Okay. Now what about py? Look, the magnitude of py was 4 meters, and I might be tempted to think this must be py, because if the length was 4 root 3 meter, this length was chosen smaller at 4 meter. I have taken the lengths proportionally. The more the length, you are aware, the more the magnitude. But then py is not 4 meters, it's minus 4. And this minus signifies that the y component of p is pointing in the minus y direction. It is not the case. I must reverse it, and I shouldn't take this and should be choosing this one. So here I go and take my py. Since it's minus 4 meters, I take it in the minus y direction. Both have their tails meeting at the origin. So this was the origin of the coordinate system. Px pointing to the right along plus x direction, py pointing downwards in minus y direction, and the resultant, because this is the reversal of, you are aware we have been given the components here, and if you need to know the angle made by p, what you need to do is that you must add up px and py, because resolution and finding resultant, they are exactly opposite processes. So px and py being known, this is your py incidentally. So let me write that. This is your py, and of course if I want to write in a vectorial way, I must give the j cap, that is j is a unit vector in the y along the y axis, and this is px into I cap, because I is a unit vector in the along the x direction. So when you add these things up, you are trying to reconstruct p from px and py. So what we have to do is, we have to complete that rectangle where px and py are the two component vectors, and we just complete that rectangle and draw the resultant of px and py is this red arrow. Now this one is of course my P vector. So if this P could be resolved, it has given me Px and Py as the component vectors. On the other hand, by reversal of the process, if Pxi and Pyj are given, I could have constructed P by applying the parallelogram rule, which in this case boils down to the rectangle rule. So that is the way we have found P, and the angle that the P makes with the plus x direction, this angle should always be measured anti-clockwise from plus x direction. So this is the angle we are talking of. This is the angle the question was asking about, this angle. Here once again I want to emphasize here, when you measure the angle made by P with the positive x direction, the angle must be measured in anti-clockwise direction, and you should not measure it in this direction. That should not be the case. So I just undo that and keep the figure as it was. So how to find out this angle theta? That's not difficult. Let me call this small angle as alpha, because the whole angle is 360 degree, and so in this triangle you are already aware the length of Px was of course 4 root 3. Length of Px, let me give some numbering here, or rather lettering. O, and I call this point say A, B. It's a right angle triangle. In this right angle triangle OAB, you find out tan alpha is given by perpendicular, that is the opposite, that is AB, divided by the base, that was OB. Now the length of AB, as you can see, it is of course Py. Now it is, when I talk about the length only, we don't consider the minus sign. This is important. Minus sign has already been taken care of in the fact that Py has been drawn in the minus y direction. But the length of an arrow cannot be negative. That's just 4 units, 4 meters. On the other hand, OB, the length is equal to the magnitude of Px, that is 4 root 3. So what we need to write here is this. This is coming out to be AB, that was 4 meters. Once again, minus sign is not sitting there because minus sign takes care of the directional part, that's downward, that's all. And OB was 4 root 3 meters, so meters cancel out, and this is coming out to be 1 upon root 3, and this you all know this is tan 30 degree. Since the figure shows alpha is an acute angle, just a value less than 90 degree, so the only possible value of alpha is 30 degree. So we conclude that the value of alpha in our figure is 30 degree, and since theta plus alpha, as the figure clearly shows, this is 360 degree, so the angle which we are looking for is 330 degree. So this is the final answer which we report. This is the angle made by the vector P with the plus x axis while the angle has been measured anticlockwise by convention. Magnitude of P was 8 meters and is directed at an angle of 330 degree with the plus x direction. Now that was the problem given. We might do the same problem without even drawing a diagram, which we can see if we have got strong knowledge and applications of trigonometry, as we shall see next. So the same problem once again without drawing a diagram and recalling our formulas of trigonometry. Let us remember the data given here. First of all, they said for the vector P, Px was given as 4 root 3 meter, and the y component Py was given as minus 4 meters. Yeah, these are the data. Now let's see how we can do that without drawing any diagram. We know that Px x component is given by the original vector multiplied by cosine of the angle theta, where theta is the angle made by the vector P with the plus x axis, the angle measured anti-clockwise. So this is Px p cos theta. Now that thing was given as 4 root 3 meter, and Py, this is given as p sine theta, as theta defined a little earlier, and this is given as minus 4 meter. Now if we call them equation number 1 and 2, you divide equation number 2 by 1, what you are getting is p sine theta by p cos theta. That is minus 4 meters divided by 4 root 3 meter. Now this is obviously coming out to be minus 1 upon root 3. Now see, the p's cancel out obviously, and sine by cos is tan. So while theta was the angle that we try to find out here, angle made by the vector p with the x-axis, then tan theta is given by minus 1 upon root 3. Now this, you know, 1 upon root 3 happens for tan 30 degree. If we took an angle that is an acute angle, tan 30 degree is 1 upon root 3. So this angle must be, I should write like this, minus tan 30 degree, because 1 upon root 3 in tan is tan 30 degree. Now here we don't draw in diagram. We try to remember the formulas of trigonometry, particularly the formulas of associated angles, the formulas on all sine, tan, cos. I think you are aware of it, but let's recall it. This is a coordinate system. You know that this is 0 degree. This is 90 degree, 180 degree, and 270 degree, and of course after one revolution that is same thing as 360 degree. As you can see from this figure, that if in the first quadrant this angle between 0 and 90 degree, all, that is sine, tan, cos, all the ratios are positive. In second quadrant here between 90 and 180 degree, sine and cosec only are positive. In the third quadrant, 180 degree to 270 degree, tan and cot are positive, while in fourth quadrant between 270 and 360 degree, only the cos and sec are positive. So we have found tan theta is minus 1 by root 2, is a negative value, which means theta should be an angle in either second quadrant or in fourth quadrant, because in first and third quadrant tan is a positive thing. So let's recall the formulas on that, which we'll be listing now. So tan, if we write tan (180 degree) minus theta, if theta is an acute angle, then that is coming out to be minus tan theta by this thing I have written earlier above. This is, you see, in second quadrant 180 minus theta, second quadrant tan is negative because only sine is positive there. So we write this is coming out to be minus tan theta. Similarly, we could have written down tan 360 degree minus theta, that's coming in fourth quadrant, as you can check here. This is the whole thing is 360 degree, and then minus theta means back into the fourth quadrant. Then again only cos is positive, so tan also is negative there. So because of that, this also is minus tan theta. So if you can know these two formulae, you can easily argue that here minus tan 30 degree can be either tan 180 degree minus 30 degree, that is tan 150 degree, or it may be tan 360 degree minus 30 degree, that is 330 degree. So we have to choose the value of theta between two possible values. One is 150 degree or the other is 330 degree. We are in dilemma. We don't know till now without the figure if the angle made by the vector P with the plus x-axis, the angle measured anti-clockwise is 150 or 330. Second quadrant or fourth quadrant. Both are possible. To get to that result, we just get back to this equations 1 and 2 earlier. Since the value of P is only positive, it has been found to be 8 meters earlier. So while Px is 4√3 meter, it points that this quantity cos theta, let me use a different thing for understanding, cos theta in this case is positive. Because Px is positive 4√3 meters, P is 8 meters positive, so cos has to be positive. While in equation number 2 tells P is 8 meters, P is minus 4 meters, so sin theta it's negative. Sin theta is negative. Equation number 2 gives me that. So when you put those two facts along with these two possible values of theta, we conclude that our answer is 330 degree. So this is the answer in fourth quadrant, because cos is positive and sine is negative, as we have found here, only happens in fourth quadrant and not in second quadrant. So we pick up this value and not this value. So this is a method of finding out the value of theta made by P with the x-axis without drawing a diagram, but as you can see, you require a strong fundamentals of trigonometry here to get to that value.